now to one of our projects within the Transformative Aeronautics Concepts program, one you just heard about there when we talked about discomfort and pushing the edges of comfort. And that program is CAS, or the Convergent Aeronautics Solutions Project. CAS explores seemingly improbable problem spaces to identify opportunities for exploration that might lead to solutions to the greatest problems that plague aviation now and into the future. We're going to kick off this block with a brief video and then head into a series of presentations with Q&As highlighting some of the work CAS has been involved in. I hope you enjoy the video. Welcome back. I would now like to introduce Tyler Hudson. Tyler is the principal investigator on a CAS effort entitled AERoBOND. Tyler, welcome to Imagine Aviation.
Thanks for having me.
As a reminder, please feel free to enter your questions for Tyler into the IO tool listed in the YouTube chat stream, as well as the Imagine Aviation website. Tyler, I'll turn it over to you for your presentation.
Absolutely. Thank you. So I'm here to talk today about a project that CAS funded called AERoBOND. And really what its focus is enabling reliable and rapid manufacturing for tomorrow's aircraft. As we all know, airframes are assemblies of many components that are brought together to make the final aircraft. And composites are lighter, they're stronger, they're more durable than metal. However, they're not really replacing metal parts as fast as they could be. And one of the reasons for that is during that assembly process. So composites can be assembled rapidly with adhesives. However, they often require redundant load pass or bolts, and each one of those fasteners are an additional step in the installation process that adds time to that to manufacturing. So really, AERoBOND is focused on addressing part of the solution of how do we make aircraft faster to meet future demand, just because our current manufacturing techniques are not going to build enough aircraft in the right amount of time to meet our demand as aviation grows. And so AERoBOND tackles that problem in a few different ways. So it eliminates the need for surface preparation, and so we'll talk a little bit about that. So we move kind of down the charts here on the right. This compares the state of art to AERoBOND. So you start with your two uncured preforms. You can think of each of these as, say, your wing skin and your stiffener or your rib. Both components, whether it's the normal way, the state-of-art way of making composites, or the way you would do it under AERoBOND, goes through a primary cure cycle. You make the two parts separately, and it's done in an identical process. The only real difference in AERoBOND is we add a layer to the surface that we're going to eventually bond it in a later step. In that next step, the state-of-art requires a surface treatment. And the reason surface treatment is needed did is we found over the years that even small amounts of contamination can cause a weak bond. And we're talking about very, very minute concentrations of contamination. Where AERoBOND, the interface itself reflows. So what that basically means is during the bonding process, the surface melts and then mixes. And so we're not concerned with any type of contamination because it gets mixed into the bulk. Then the assembly process itself is identical. So the way typical, like your rib and your wing skin we brought together, they're brought into contact. A layer of adhesive is placed in between. In AERoBOND, we do the same process. So you have your wing, you have your rib, and you put this adjoining layer B or the AERoBOND material in place of the adhesive. And then what happens in that final step is you wind up with a co-cured structure. So those two parts have become essentially one part. Even though you made them separately, chemically and mechanically, they are a single structure when you're complete. And the reason that is so transformative is it removes the need for redundant fasteners or redundant load paths because you've increased the reliability of the joint. So you take that whole bolt installation step out of the manufacturing process for certain components on the aircraft. And what that really results in is a fabrication process that is about 40% faster than the state of art, about 10% lighter. It can be more or less according to what components they are, how large, how many bolts. And you get all of that with an equivalent or improved mechanical properties. And so we've done a suite of manufacturing or mechanical property tests. So we've looked at fracture toughness, both in shear and tension. We've looked at strength, both in shear and in tension. We've looked at damage tolerance. We've looked at impact resistance. And across all of these different types of properties, we're seeing the AERoBOND competes and often beats the traditional co-cured laminates. And so that's really AERoBOND as a whole. Steve, you have any questions about AERoBOND?
Yeah, absolutely. There's some starting to pour into the chat now, but I think how do the mechanical properties stack up against the traditional co-cure? I mean, you touched a little bit about that, but can you expand a little bit more on that?
Yeah, absolutely. So across the board, so when we set out to when we pitched this to CAS, we actually pitched it and said we think in 2 years, which is extremely fast for materials development, we think we can get to 80% of the state of the art. That's kind of where we would be happy. If we get to 80%, we can check our box in mechanical properties, and just knowing that there's nothing theoretically that would prevent us going higher than that, but we thought that's realistic where we maybe can get to in 2 years. Well, at the very end, we kind of surprised ourselves. We were equivalent across the board, and then specifically in shear, we actually found that AERoBOND was consistently stronger than the state of the art. And we have some reasons behind basically the way the reflow process works. You get a little bit more almost like bedding of the two structures, and that really improves the shear properties specifically.
So why you talked about the curing parts? Why would you not co-cure every part?
Yeah, that's a great question, because that's always one that comes up. Is like, why would you go through all this process if you could just make it in one shot? Well, the short answer is it's impossible. You could imagine trying to make an entire aircraft as one component. The tooling would be so complex that you couldn't even fabricate the tooling. On top of, you couldn't get the tooling out because you have all these internal components that you're trying to make. And so it's just completely unrealistic to make an entire aircraft in one component. That said, this very reason is why you hear so much about unitization. So why different airframe manufacturers are constantly trying to reduce part count. How many things can we possibly combine so we don't have to worry about this assembly step? It's a real headache for manufacturers trying to bring components together to make an aircraft.
Yeah, that does make a lot of sense. What I assume is the complete opposite of the headaches is the 40% gain, or the numbers you were mentioning in the manufacturing rate. Can you touch a little bit more on the exact number? I might be miscoding you, and how you came up with those, and the excitement from manufacturers on that topic.
Yes, absolutely. So that primarily comes from the two components that AERoBOND removes. So the first is surface treatment. So if you look at a composites lab, you're out and you're making these components. Silicone specifically is terrible, and it is everywhere. Silicone is in pretty much anything in a composites lab. It's in your release agents, it's in your peel plies, it's in the backing paper. We actually, kind of the anecdote was, we used to do contamination studies where we would intentionally add contamination. And then what we found was we didn't need to add contamination. If we just went and built something, it was going to be contaminated. There's just too much out in a manufacturing facility that is used as part of the process. It's not like you have a dirty lab. It's like it's part of the process. And so there are multiple ways to remove contamination, whether it's grip blast or laser ablation or plasma. But all of those take time, and being able to completely eliminate that portion is a savings in and of itself. And then the other piece is the bolt installation. And by no means are we saying that you're going to fly an entire aircraft with the no bolts. That's not what we're saying. But where we are targeting are the redundant fasteners, or the chicken rivets, that you hear people talking about. It's those that the only reason they are there is because you cannot trust your bond. Your bond is completely strong enough, but just in case we need it. We're trying to remove the need for that just in case, because it's co-cured, because it's reflowed, because it's inspectable. You can pull out some of those redundant fasteners.
Really fascinating. I would assume any significant change like this is going to run into some certification issues. So have you stumbled or begin to foresee any additional certification processes AERoBOND might have to go through in order to attain flight worthiness?
Yes, absolutely. So CAS, and we've heard a lot about what CAS is, but CAS is high risk, high reward, short turnaround. So you're talking about 2 years. Sprint, go as fast as you can. And the goal in CAS is to prove feasibility. Can this be done? I think we actually went a little bit past feasible but that is the first step into making it onto a flying aircraft. So first you've got to prove that something can be done. That's what CAS is all about. Then you have the commercialization, and I think we'll hit on commercialization a little bit more after, but that's really where AERoBOND is at now. And then the next step after commercialization is, once you have a customer that says, I want to fly this, then you start the process of, okay, what steps are needed to actually certify. So we talked about all the mechanical properties that we measured. Well, how do we turn those mechanical properties that we've already measured into A basis and B basis allowables, so that a design engineer could design a structure that's made this way? And so that's really kind of one step past what, no CAS project is ever going to be like, get something where it can fly on an aircraft in 2 years. Like, that's not what CAS is about.
Well, and then there's a question in the chat that you might have already begun to answer, but AERoBOND sounds great. Why isn't everyone using it right away? What are the gotchas in it? So other than the timing and the proving of it, what other things might be cautionary stumbling blocks that you want to pay attention to going forward?
Yes, absolutely. So one is it's really new. We're talking about it's in the last 5 years. So that's one reason that no one is using it yet. The other is for so long, the way we've made composite aircraft is you bring them together, you put adhesive, and then you put bolts. Like that's just we know, even though it's very difficult, we know how to do it. And it is a new way to assemble aircraft. And so if you're not wanting to take that risk to do a new process, that would be a potential kind of roadblock, is just adoption by manufacturers on wanting to go this route.
That's great, and it also does make me believe your last few answers is, where do we want to go with AERoBOND? What transition opportunities have you discovered as you've been exploring this?
Yes, absolutely, and I'll commend CAS. When we started, they had actually brought in a transition manager, and so like every month we had to talk with her about, okay, what are we doing for transition? And like we're trying to make it work. Let's hold off a little bit. But we as much as we like that pull, we were also very happy because on the backside of AERoBOND, inside that 2 years, we transitioned into 2 NASA internal projects. So one is in one of the other aeronautics programs, but the other you're actually about to hear from. The Susan aircraft that, and I won't steal any of their thunder, but we're looking at using, we're investigating, we're still identifying where on the aircraft, but we're investigating using AERoBOND to assemble a few of the composite components on the Susan aircraft. So that's internal to NASA. We're very excited about that because that would be flight experience in an unmanned aircraft inside a NASA project, and that's just building that confidence in the technology. But then also externally, we've had a few partners already come to NASA's technology transfer group and say we want to license this, and we're really excited to see it transition both internal and external in a 2 years is just really fast for a materials project.
Yeah, I think that's part of the wonderful excitement about this, is that how quickly this has come. And one of your responses there regarding Susan kind of spurred a question that I saw in the chat is, are AERoBOND techniques mature enough to build a typical aerospace structure, such as a wing section, or to take the technology to a higher TRL level?
Yeah, so that is something we're actually very thankful for Susan for. It is moving us out of the build, or it's moving us up that building block. So we made a underneath AERoBOND, we did have a capstone kind of project that was a skin siphon panel. So it was a very realistic chunk of a wing. That's how that was, like I said, our capstone project under AERoBOND. But Susan is taking it to, and the next step is we now have to not find a representative part. We have to go onto an aircraft, it's a 25% scale, and find 2 components that we want to assemble, with AERoBOND. And that's kind of that next step that, and we're figuring out where it's most appropriate and where it isn't. Really looking forward to seeing how that turns out in the next few years.
Right. Looking forward, and this might be a harder question, but maybe your team have given it some thoughts. But when you think about this in production, would vehicles using AERoBOND need different maintenance over the years than traditional aircraft assembly?
No. One advantage though is, and we really don't have time to really get into why, but they're more easily inspectable by traditional NDE techniques. So that would be one piece that would make it. You're gonna have to still do everything that you would normally do on a structure, but you do have a little bit of flexibility in being able to inspect them easier than a traditional bonded laminate. And that is, you would never went through all of this work just to get to that, for that piece, but it is it's a nice add-on, right at the, to kind of tack on the little bit of benefit.
Right, absolutely. There's a technical question. I don't know if you can answer it or if you have the data with you, but talking about cure temperatures, what is the cure temperature? Is this hot, wet performance good, or
Oh no, that's a great question. So we were using traditional aerospace grade materials. So these are 350F toughened, 350 Fahrenheit cure toughened epoxy components. If you go out and look at like what the composite aircraft that are flying now, we were buying commercial materials as our component materials, and then the assembly technique is right in line with either a 250 or a 350F cure, which is very kind of standard operating temperature ranges.
All of this that we've talked about is horribly exciting, and especially as you think about not only the speed of what you've done this, but the revolutionary reduction of production time and therefore cost savings for airframe manufacturers. The potential for this is wonderful. How are you making aircraft companies, especially the smaller ones, maybe to start, aware of this technology?
Events like this are definitely a component to it. We also published a lot during AERoBOND. We also presented at a lot of conferences. So one of the kind of side benefits to all of the conferences going virtual is we could attend more. Because we weren't spending a week, off site every time. Now, I think we need to get back to in person because I think there's something lost in a virtual conference. That's for a conversation for another day. But what it did allow for during AERoBOND's execution is I think we had like 10 or 11 conference presentations in a year. So we were essentially going to a conference every month and talking about AERoBOND. And so that was really the ways we were looking at getting the word out. And then also one of the inquiries from the tech transfer, we had nothing to do with the reaching out, or it was nothing external. They came to us. They had seen it in a paper or in NASA's tech transfer office or something along those lines, and they reached out. So it was nothing that we did.
What's the biggest barrier you think you face with an activity such as AERoBOND and with furthering these maturing technologies?
Yeah, it's really, and this is an age-old where technologies go to die. Is how do you take it from you've proved it's feasible, you're in that TRL 4 to 6 range, how do you get it to 7 to 9? Like getting someone that is building lots of aircraft to say, I want to take this technology that you've developed and I want to put it on the next aircraft that's flying. This is not new to AERoBOND. It's a hard thing to walk up that full TRL spectrum.
Right. I would assume it would be. If you think about Tyler, we heard this morning of Catherine and John talk about uncomfortable and making people uncomfortable. You're introducing a technology that is quite different than the way airframes have been built for how many decades, and built successfully and profitably for so many decades. When you think about being uncomfortable or forcing discomfort on others, what inspires you about the work you're doing? What inspires you about the work you're doing, the work your team's doing, and how that can really influence and alter civil aviation going forward?
Yeah, I think NASA is just well positioned. I feel like internally we don't really have to convince each other that this is what we should be doing. I think all of us, strive every day to work on things that matter. If it's not gonna make a difference, like why would we want to work on it? You maybe contribute that to NASA's culture, which I think is really good. But I think that's actually pretty easy, especially at a research center. I work at Langley Research Center, so we're constantly doing the uncomfortable. So I don't think we have to go out of our way to foster it.
Oh, that is great. Tyler, I love speaking to you about this effort. We really want to thank you for your time. Thank you for your energy, for your work on this, and spending time for us to answer some of these questions. So thank you very much, Tyler.
Thanks, Steve.
Next, we want to take you to a video highlighting another CAS effort, the subsonic single aft engine, or SUSAN. Enjoy the video.